to projects. In this video, we are going to explain about the project that is enhancing software fault prediction through feature selection with Spider Wasp optimization algorithm. Before getting into the execution, first let us understand what is the project about. Software systems are everywhere today and they are crucial to many areas like healthcare, finance, transportation, and communication. These systems do a lot of important work, but they aren't perfect and can experience faults that can cause serious issues like system crashes, data loss, or even security breaches. When these problems occur, they can lead to significant costs and disruptions. That is why it is so important to catch software faults early on. Software fault prediction is a method used to predict where fault might occur in a software system before they cause any harm. By identifying potential problems early, developers they can fix them before they lead to bigger issues. This prediction is done using variety of techniques like statistical analysis, machine learning algorithms, or even combination of both. These approaches helps to make the process of finding and fixing faults more accurate and efficient, ultimately improving the overall quality of the software and reducing cost in the long run. And software prediction, that is software fault prediction, is difficult task because modern software systems are complex. These systems are made up of many components that interact in different ways and their behavior can change depending on various conditions. This makes it hard to predict where faults might occur. One important step in improving software fault prediction is feature selection, which is the process of identifying the most relevant features or data points that can help make better decisions. By focusing on these key features, we can make prediction process more accurate and efficient. However, the existing methods for selecting these features like filter based, wrapper based, and embedding techniques have their own problems. They can be computationally expensive, prone to overfitting, which means they perform well on training data but not on the new data, and often struggle to generalize well. To tackle these issues, optimization algorithms like particle swarm optimization and genetic algorithms, that is GA, are used. But they also have their drawbacks. These algorithms need a lot of fine tuning and can sometimes get stuck in local optima. Basically, they might find a good solution but not the best possible one. This shows that there is a need for better, more efficient technique to select the right features for SFP, that is software fault prediction, reducing both computational costs and also improving the prediction quality. So, to overcome with all these issues, the proposed system aims to enhance software fault prediction, that is SFP, by using a unique algorithm called Spider Wasp optimization algorithm for feature selection. This algorithm is inspired by hunting behavior of spiders and wasps, where they carefully select their targets based on specific patterns. Similarly, SWO identifies the most important features from the KC1 dataset that we have used in this project for detecting the software faults. So from this dataset, important features will be selected, focusing on those that truly contribute to predicting the faults in software systems. It eliminates irrelevant or highly correlated features. So by using this SWO algorithm, it eliminates the unnecessary features that could complicate or reduce the importance of machine learning models. So by keeping only the essential features, SWO algorithm improves the model accuracy and also the efficiency, making the fault prediction process more reliable. Once the relevant features are selected using the spider wasp optimization, that is SWO algorithm, various machine learning models that are decision tree, naive bayes, k nearest neighbor, and latent dirichlet analysis are trained using these optimized features. The goal here is to assess how well these models perform when they are provided with the best possible data for prediction. And their performance is evaluated using accuracy, precision, recall, and FN score. So their performance is evaluated primarily based on accuracy, and the results are compared to those obtained using traditional features by genetic algorithm. So features extracted from genetic algorithm, which is a traditional model, are compared with the features extracted using this SWO algorithm. So by using SWO for feature selection, the system not only improves the accuracy of the predictions but also reduces the computational load, making it more efficient approach for software fault prediction. It is a balance between getting accurate results and keeping the system lightweight, which is a key for practical applications. So, to further enhance the performance, in this project, we have employed XGBoost algorithm, which is an ensemble method known for its powerful performance, especially combined with parameter tuning. This helps to boost the accuracy of predictions even further, no matter which sets the features we are using, whether it is all features, the ones selected by genetic algorithm or ones chosen by the spider wasp optimization. The results are consistently better across the board. Additionally, the front end of the project, that is user interface, has been built using Flash framework. This allows users to test the system directly with the secure authentication, ensuring that only authorized users can interact with it. This setup not only makes the system more accessible but also allows users to actively assess its performance, improving their experience and provide valuable feedback. Moving on to the implementation. To implement this project, we have followed the steps mentioned in the flow of work. So first, the necessary libraries and packages such as pandas, numpy, sklearn, and matplotlib are imported to handle the data manipulation, machine learning, and visualization tasks. Then comes the exploring the dataset. The dataset is loaded, examined to understand its structure, checking for missing values, and identifying potential issues. This step helps in understanding the data's features and target variables. Then comes data visualization. So visual tools like graphs, histograms, scatter plots are used to explore relationship between features, identifying patterns, and gain insights into the data. Then comes data processing. So here we remove duplicate records. Duplicate records are removed to ensure that data set is clean and accurate. Then comes drop cleaning. Irrelevant or missing data is dropped to ensure the model focuses on meaningful features. Then comes feature selection. So here we have selected features using two algorithms. One is spider wasp optimization algorithm, and for the comparison that how well this proposed model is working, we have also incorporated the traditional model that is called genetic algorithm, an evolutionary algorithm that selects features based on principles of natural selection. And then comes selecting X and Y data. So here the data set is divided into input features and target variable. Input features as X and target variable as Y that the model will predict. Then comes splitting the data set part. So the data set is split into training and testing sets. Training set is used to train the model and testing set is used to evaluate its performance. Then comes building the model. So here we initiate the model. So here we will be initiating and defining the model. After defining, we will be training it with the training data to learn its parameters, features for predicting the software fault prediction. So here the model is trained using the training data where it learns the relationship between features and the target variable for predicting the software fault. Then comes comparison of the model. So here we have compared all the models built using accuracy, precision, recall, and FN score, and we have compared them through the scores of all these models. And then coming to the part of front end. So a front end interface is built using Flash framework, allowing users to interact with the system. SQLite is used for storing user credentials and managing authentication. And in the front end, users they can input feature values for the prediction through the front end interface, providing new data for the model to make predictions. And that will be pre-processed at the back end. It will be fed with the trained model. Finally, outcome will be displayed through the front end, whether software is fault or non-fault. Moving on to the algorithms used. So here we have used naive Bayes, KNN, decision tree, LDA, and extension XGBoost model have been used for predicting the software faults. So all these models are trained on the features extracted from spider wasp optimization and also the genetic algorithm. So here, for example, this naive Bayes algorithm. So this naive Bayes algorithm has been trained on the features extracted using spider web optimization and also the features extracted from the genetic algorithm. Accordingly, all the models are trained using genetic and also the SWO algorithm. So coming to the requirements to implement this project, we need hardware and software requirements that are operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let us execute. To execute, we are supposed to open the code folder that contains source code files. So these are the source code files in the code folder of the project. Let us understand each of them. How will they be used in this project? So first, let's open the dataset folder. Here we have two subfiles. One is KSE1 and the other one is test data. So this is the main dataset that is used to train the models for predicting the software fault. Let's open this. Just wait for a while. It's being loaded. So here is the dataset. This is the dataset that is used in this project to train the models for predicting the software fault. So here are all the different features. So these are the features that are used Based on these only, software fault will be detected. So this is the target variable where we have class 0 and class 1. Class 0 refers to no fault and 1 refers to there is the fault. Let's close this. And here in this test data, we have the test cases that we will be using in the front end for predicting the software fault. Get back. And here in this model folder, we have the algorithm information that is stored in .h5 files, numpy files, pickle files, and that will be loaded into the project code during runtime of the application. And here we have static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And then comes the templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And then we have app.py file. This .py file contains the information related to front-end logic. And it includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the signup.db file. This file is a database file which is used to store the information. And this is the Jupyter Notebook file, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So this is about the code folder. Now let us execute. To execute, copy the path of the code folder from the address bar of the file explorer. So copy the path. Now open the command prompt. It has been opened. Give the command cd, give the space, and paste the path. Now click on enter. Here, if you observe, current directory is changed to the code folders path. Here, if you observe, by giving this command and specifying the path, it has changed to the code folders path. Now compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here. Click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So here you can see a sign up link, right? We need to click on that. So click on it and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on click here and give your username and the password. So I'm giving my username and the password. Click on login. We have logged in successfully and we are redirected to prediction page of the project. Here you can see a choose file button, right? Click on that for uploading the test case. So this is the test case that we're supposed to upload. Select it, click on open. And before uploading, let's see what do we have in that test case file. So open the test data. So here are different test cases that now we will be giving them as the input for predicting the software fault. Let's understand each of them. That is each parameter. First we have is a log. It is the line of the code that the total number of lines in the software code, excluding blank and comment lines. It indicates the size of the code base. Then we have VG, that is cyclomatic complexity. It is a metric that measures the complexity of a program by counting the number of linearly independent paths through its source code. It helps to assess the software's maintainability and testability. Then we have EVG, that is essential complexity. So it is a measure of the program's complexity that excludes the impact of structured programs, constructs like loops, conditionals, etc. And it indicates the complexity of program's logic. Then we have IVG, it is the intermediate complexity. It is a measure of complexity that quantifies the number of decision points in the program, but it isn't as refined as essential complexity. It provides a general sense of the program structure. Then we have N. N is the number of functions. It is the total count of functions or methods in a software. More functions often suggest a more modular or complex system. Then we have V. It is the number of variables. It is the total number of variables in a software which can give an idea of the program's complexity in terms of memory management. Then we have I. It is the number of loops. The total number of loop structures in the software, for example, while. So more loops usually indicate higher complexity and risk of false. Then comes D. It is the depth of inheritance. It is the depth of class inheritance in object oriented programming. A deeper inheritance structure typically leads to more complex and harder to maintain code. Then we have I, it is the number of interfaces. It is the total number of, that is total count of interfaces in object oriented programming, which represent the abstract definitions of behavior that are implemented by a class. E. E is the number of expectations. The total number of expectations, exceptions handling structure, that is try catch logs. A higher number of might indicate a greater error handling complexity. Then we have B. It is the number of branches. The number of decision points in the code, that is if else, switch case, etc. More branches generally increase the complexity of the software. Then we have T. It is the number of tests. The total number of test cases written for the software, which can help determine how thoroughly the software is tested. Then we have I code. I code is the lines of the code in comments. It is the number of lines in the code that are comments. It can give an indication of how well documented the code is. Then we have IO comment. It is the lines of comments. Similar to the above, that is similar to the IO code, it specifically it is the specifically number of comment lines in the code. Then we have IO blank. It is a line of blank code, the number of blank lines in the code which can indicate code organization or the readability. Then we have IO code and comment. So this is the IO code and comment. It is a line of code and comments, the combined number of lines containing either code or comments, providing a broader measure of the overall content in the source code. Then we have unique OP, that is unique operations. It is a count of distinct operations, that is example arithmetical or logical using in software. This can give an idea of the diversity of operations in the code. Then we have unique operand, that is unique operands. They are the count of distinct operands, that is variables, constants, etc., used in operations, which helps to understand the variety of the inputs in the software. Then we have total op, that is total operations. They are the total number of operations, including types, present in the code, indicating the overall activity level of the software. Then comes total operands. So here it is the total operands, and last we have is the branch count. Here it is the total number of branching structures such as if else and switch statements in the code. This is a key indicator of control flow complexity. So these are the inputs that we're going to give now. So these are different inputs. Total we have 20 parameters, and for these 20 parameters we have multiple test cases that we will be giving them as input. So now we will be giving total these many test cases. Now let's upload the file, get back to the application and click on upload. So this given input, it will be pre-processed at the backend, and then train model will be giving us a prediction. So this is the first case that we have given. For the first case here, we got the prediction as no false for the given input feature. So this is the input feature of the fault, that is software. So for this, we got the prediction as no false. That means there are no faults in that software. And for the second software also, that means for the second case for that software, that these are the inputs. Here we got the prediction as no false. And for the third one also no false, fourth one no false, fifth one no false. And for the sixth one, so this is the sixth software, sixth test case that we have given as input. For this case, here we got the prediction as fault. That means there is fault in that particular software. Moving on to this, I mean, seventh test case, here we got the prediction as no false, and for this case also no false. Similarly, and for this case, so here if you observe, for this case, here we got the prediction as fault. Accordingly, for all the test cases that we have uploaded, the train model has given the prediction whether there is software fault or not. If there is fault, it has given that fault. If there is no fault, it has predicted as no fault. Now let's check with the graphs. Click on graph. So here, the first graph which we have is the sample outcome graph. This shows the class distribution of the target class of this project. Here on x-axis, we have dataset class label, and on y-axis, we have the count. Here, this bar represents no false and this bar represents the false. Here if you observe, no false cases are more than the false one. Moving on. So this is the accuracy comparison graph. Here on x-axis we have accuracy score, and on y-axis we have all the algorithms trained on the all features. Here this graph, these algorithms are trained on the complete data set where feature selection technique has not been used. And here this is the genetic algorithm all the algorithms are trained on the genetic algorithm extracted features. So here on x-axis we have accuracy score, and on y-axis we have all the algorithms which are trained on the genetic algorithm extracted, that is selected features. And here we have SWO accuracy score graph. Here on x-axis we have accuracy score, and on y-axis all the algorithm names. So these are the algorithms that are trained on the data set where features are extracted, selected through this proposed SW, that is spider wasp optimization technique. So these are the metrics used. Now click on sign out. In this widget, by giving input to the application, if there is fault, the application will predict there is fault in the application. If there is no fault, the application will predict that there is no fault in that application. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.